In this video, we're finishing the proof of the extreme value theorem. I want to remind you where we left off last time. We have a function f, which is continuous on an interval ab, a closed interval ab, and we're trying to prove that it obtains a maximum at some point between a and b. Perhaps it's equal to a or equal to b or somewhere in between. We have a point x naught, and the value of f at this point x naught is higher here, greater than or equal to any other value. So we have this inequality, f of x is less than or equal to f of x naught. So x naught is then called a maximum or global maximum for the function f. And the content of this theorem is that if f is continuous on a closed interval, then it will at least have some global maximum value. Now we're sort of in a sense halfway there. We've proven that the set of output values of f is at least bounded above and therefore has a supremum. Now, that is, it doesn't go off to infinity. There are not ever larger values of f awaiting here. Now, that's not sufficient because even though the set is bounded above and has a supremum, in theory, it could not obtain that supremum. It could have values of f that get closer and closer and closer and closer to whatever that value is. Maybe this is 10, maybe we get values 9.9, 9.99, closer and closer to that value, but maybe that value itself is not obtained. Maybe there's no x0 value that actually obtains that special value. So what we need to do here, what we need to do next is we need to identify that value and prove that some x naught here actually does obtain that value. So here's what we're going to do. We're going to, let's let S be the supremum of the values of f of x where x is in the closed interval a, b. Now, first of all, then S is a real number. It's not positive infinity. This supremum exists because the set is bounded. So this is because the set is bounded above. This is the content of what we showed in the first video, that this set of output values is at least bounded above. So what we need to do next is we need to show that S is actually obtained. So what we're going to do here, we're going to claim there exists an x naught in the interval so that f of x naught is equal to S. We don't necessarily know up front that there is an x naught such that f of x naught equals S, but we do know that we can get values of f very close to S because S is the supremum of all of the values of f of x. So we know that however close we want to get to S, there is some value f of x which is that close. In other words, so let's state this precisely. So because S is the supremum of that set, then there are closer and closer values. So for any epsilon greater than 0, there is some element of that set, some f of x, such that f of x exceeds S minus epsilon. So we'll think about this on a number line, but because we're thinking of these as vertical values, let's put the number line vertically. So we have I'm just going to draw an illustration of what we're doing here. We have the range of f of x, and then we have this value S, which potentially is not obtained, and so that's why I'm giving that an open circle there. So if we subtract epsilon from that, so that's a distance of epsilon, and then here we'll get a value S minus epsilon. If we subtract epsilon from that, then somewhere in here between S minus epsilon and S, there must be some value f of x. Otherwise, S minus epsilon would have been an upper bound for the set, and then S couldn't be the lowest upper bound for this set. So if you back off a little bit from the supremum, then you're always going to have some value greater than that value, S minus epsilon. So what we're going to do is we're going to select a whole lot of such values, and we're going to make them get closer and closer to the value S. To be precise, for any n in the naturals, what we're going to do is we're going to choose an x so that f of x exceeds s minus 1 over n. So basically, in place of epsilon here, I'm using 1 over n. 1 over n will be a small number, and if n is very large, it will be a very small number. And so f of x will be chosen to be very close to s. Now, because this choice of x is a different choice for every little n, we should index it with a little n. So we're actually choosing x sub n so that f of x sub n is going to be greater than s minus 1 over n. Now, where will this value be chosen? It will have to be chosen in the domain, of course, and so we're going to choose it in this domain AB. So we're choosing not one x value, but many x values, one for each n, and this will mean that we've actually, in effect, chosen a sequence. So notice also that f of xn has to be less than or equal to s. This should be obvious because s, oops, I wrote that wrong, f of xn, like that, has to be less than or equal to s. This should be obvious because s is the supremum of all of these values, and so it is in particular an upper bound for all of these values, so you can't get better than that. So we have f of xn in between s and s minus 1 over n. So what we can do then, if we have a sandwiched, let me write it this way, between s and s minus 1 over n, if we have f of xn between these two values, then we can apply the squeeze theorem. Notice that this is a sequence, depending on n, which converges to s. And this can be regarded as a constant sequence, which converges to s. And this is a sequence of values that lies in between this convergence sequence and this convergence sequence. And we don't know that it converges, except the squeeze theorem will tell us that it does, because these things converge to the same thing. So let's immediately conclude by the squeeze theorem, since this sequence converges to s, and this sequence converges to s, and this sequence is trapped in between, the sequence f of xn, excuse me, converges to s. Which, I mean, of course it does, right? Because we've been decreasing the epsilon value and then choosing an f of x value in between, like, s minus 1 over 1, s minus 1 over 2, s minus 1 over 3, s minus 1 over 4. And so they're getting closer and closer to s. So of course they are. So we have the f of xn's converge to s. Now, what does the sequence xn do? So this is where you should be starting to have a little bit of deja vu. This half of the proof is very like the first half of the proof. We have the sequence f of xn that behaves in an entirely predictable way. Last time it went to infinity. Then we have the sequence xn, and that behaves in a completely unpredictable way because I've just chosen some xn value in between a and b, but I don't know where, and I don't know that there's any rhyme or reason to how these things sort out. I don't know that each one is bigger or lesser than the previous. I really don't have any idea what's going on with the values of the xn's compared to each other. So it's kind of strange here. The x values are less predictable and the f of x values are more predictable. But never mind, this sequence xn is at least a bounded sequence. So we can at least record that. So the sequence xn is bounded. And so we're going to do exactly what we did last time. If it's bounded, then it has a bounded monotone subsequence. This is because every sequence has a monotone subsequence. And so if this one is bounded, then then a monotone subsequence of that is also bounded. So it has a monotone bounded subsequence. And that subsequence we're going to call Tn, just like last time. Tn, and that's a subsequence of the xn's. So Tn is going to be inside the domain AB. And that monotone bounded subsequence, by the theorem called the monotone bounded sequence convergence theorem, that thing converges, right? Any monotone bounded sequence converges. I should have said here subsequence. So the Tn's are a subsequence of the xn's. So this thing converges by that theorem. And if it converges, then let's give its limit a name. Let's call it capital T, as before. So in other words, when we say the limit of Tn, that's going to be T. Now let's apply sequential continuity to this statement. This is a sequence of x values converging to this x value. If we apply sequential continuity, then we'll get a sequence of y values converging to f of that. So let's apply sequential continuity first. So by sequential continuity, then we get the limit of the f of tn's is equal to f of t. And that's, of course, the limit as n goes to infinity. So that's what sequential continuity tells us. But the limit of the f of tn's, this is a subsequence of the limit of the f of xn's. And we already know that f of xn is a sequence that converges to s. And so this subsequence of the f of xn's must likewise converge to s. So let's record that. So the limit of this equals s, and that's because the f of tn is a subsequence of the f of xn's. So that's a subsequence of the sequence of f of xn's, which we already discussed converges to s. And so if this limit is equal to f of t and this limit is also equal to s, then what do we conclude? We conclude that f of t is equal to s. So what? So we have some value. So this is the s here. So what we've done is we've identified some value t, and f of t is equal to s, which, okay, so that was the thing also referred to as x naught here. So we found some x value, namely this t, which is the limit of the subsequence of the tn's. We've found some x value such that when f is applied to that x value, we get the supremum. That proves that the supremum is, in fact, achieved. And because it's the supremum, then it has to be the maximum value. So this proves the extreme value theorem, at least as it applies to the maximum value. This proves that any function on a closed interval, if it is continuous, then it achieves a global maximum value. You might think that we're only halfway done, and we still have to prove the extreme value theorem for a minimum value. This is not really difficult. If you're concerned about the question of the minimum value, then all we need to do is just take the entire function f and flip it upside down by considering negative f. Then take a maximum of negative f, and that will give us a minimum for f. So it's pretty easy to deduce the minimum statement from the maximum statement. And that concludes the extreme value theorem.